Good evening. This is the last of the lectures organised by Technical Studies this year, and I'm very pleased that I think we'll be going out with a bang, as they say. Now, I'm very delighted to introduce Uli Knaack from, I dare not ask you about my Knacker, from Germany, who is going to talk about glass constructions. And before I say a little more about him, I want to remind you that he has very kindly agreed to do a workshop tomorrow morning as well, between 10 and 12, up on the diploma unit floor. And the idea is that students just come along with their projects, with some work, and discuss them. Now, Uli is an expert on glass, and his work building with students, when he works with them, he likes them to get to know glass very thoroughly and how it feels. He is going to talk to you about that work to begin with, and then he's going to talk about 4 projects. He's going to show you 4 projects that he's been developing, and he's going to talk about their detail as well. And he is working at the moment with funding, I think, from the German Science Foundation on glass and structure, and new projects looking at new potential structural systems, glass structural systems such as glued fixings, and this forms the basis of his PhD thesis, on which he's also working at the moment. So, with no further ado, I'm very pleased to introduce Uli Knaack.
Right. I'm not very good in English. I wasn't very good in school, so I'm sorry about my maybe bad English. This is the first lecture in English, so it's maybe a bit difficult, and I always need to read because, well, when I do it in German, I can just run around because I know the slides, but here it's a bit difficult. First slides, please. All this equipment here. Blue buttons. There they go. The desire to decompose space edges to get more architectural transparency does exist since a long time. The Gothic style has done the first step into this direction with their filigree structures. The Gothic choir of the cathedral in Amiens. Next slides, please. Oh, well, I got to do it here. With the development of new glass products, new steel products, still fascinating glass pellets were developed with filigree construction, so that the space aged could start to disappear. The samples I show is the College Museum in Oxford and the Airport Hotel in London, which shows the difference between the last 100 years. Left side, a cast iron system, right side, and bolt-holded glass facade, the systems where we are now. With this lecture, I try to give an overview of glass construction, structuring the whole thing with examples of load-bearing structures, because, apart from the architectural concept, the structure affects the filigranity of the glass systems and the appearance. This technology is only usable with clear understanding of the methods. So I distinction construction after their system. Glass is used as a roofing, as a cladding, or glass is used as a load-bearing structural element. Structurals in generally are getting more filigree, getting more transparency, when you're able to minimize the structural mass. Means get away from torsion systems, try to get hybrid systems, torsion and normal forces, or try to get best normal forces systems. first way. Second way, activating the geometry of the structure from single-layered structures to double-layered structures. The top one is a single-layered beam structure. The next one is a truss, double-layered beam structure, and then a truss structure. Activating the geometry means getting arch construction or barrel construction, or the best way to get the mass down from the structural mass down is cable constructions, because cables don't have the problem of bending, and so it's the best way to get really filigree systems. Historical glass construction. The technology progress of ironwork and glass products of the last century is related to the Industrial Revolution. 1830, new railways needed to be done, and a new dimension of bridge construction was done. So the steel, the iron was developed a lot. Second thing, fully glazed greenhouses had been necessary to protect the tropical plants which did come from the colonies. These two slides show the hot house and the palm tempered house in Edinburgh from 1830 and 1856. It does show two generations of greenhouses. I'd like this picture very much because this is an old greenhouse with an timber roof construction which was taken away. Then they built this greenhouse with a cast iron construction. The system is a glass roof and then large windows in the facade, but still it's a Victorian type of facade. Next. Well, here you see a view through the glass roof, and what happens here, glass is stiffen the whole system. You see the bars here and then the glass panels, but there are no cross bars. So every bar is stiffened by the glass panel which lays in putty. Putty, I think, is the right word, I hope. Well, the next step must be to get away from the massive building, try to build complete glass houses. This is Kew Garden in London, and again, there are no crossbars. The glass panels stiffen the whole system 15 times of the possible glass size, made the grid, and then each glass panel stiffens each bit of the bars, so no crossbars, and the whole system is just reinforced with an iron cable around the whole structure. So every glass panel is fixed together. Well, this is an inner view. You can see there's no crossbars. The project where you can see best that glass really stiffens the system is Kibble Palace in Glasgow. They made a scaffolding put on every bar, and then the glass is fixed. They took down the scaffolding, and the whole system just moves a bit. And you can see this because these bars are not straight, they're curved. So the whole system just gets down 4 centimeters. The glass takes the forces of the system, and then the thing stands up, which is very John Kibble could be very proud of this project because, they don't really know what happens. They just do it by feeling, and then the whole thing works and fine, and the project was in good economy. I hope. Glass structures are not thinkable without this project, Picton Garden in Devon. It's unknown who designed it. It's done after the Luden's concept. Again, profiled cast iron bars stabilized with glass panels. It's standing since 150 years without major damage. The paraboloid form is optimal in 2 ways. The first way, and that's the way it is thought, is to catch as much sunlight as possible. So for the whole day, the sun is always right angled on a bit of glass, so that the sun really can get into the greenhouse for the whole day. But the second way, which is interesting from the structural point of view, is that a polygon form polycomb shape is optimal for the internal flows of loads in the system. So these two things come together and made a really perfect glass house. Also, glass houses are not thinkable without Joseph Paxton. Here, one of his first great projects, the Great Greenhouse at Chetworth, an arch construction out of laminated timber and cast iron columns. And it was closed with the ridge and ferro roof. Ridge and ferro roof are two glass panels leaned to each other, so they're bearing themselves. They are in structural use. And they are thought not, again, from the structural necessities. They are thought from the gardener mind, because, again, glass is right-angled to the sun, so the morning and the afternoon sun always gets through the system, through the glass in the greenhouse. The most impressive glass building, and also it was essential for the acceptance of glass construction in society of the last century, is Crystal Palace. Only possible because of the glass projects before, like the Great Greenhouse in Chatsworth. For the World Exhibition 1851 in London, Joseph Paxton, an engineer and gardener and open-minded thinker, who knows and had the contact to the different people who build the thing, and that makes this one thing possible. They created this because of lots of time problems. Well, I think you will know this. Glass, again, is used as a ridge and ferro roof on laminated timber beams and cast iron columns. But load-bearing glass construction are thought by a feeling for the material, by not acknowledgement by doing it, but just feeling how it may be work and then try and error. And also a necessity of economy, because the people who did the glass buildings, the glass greenhouses, are always the undertaker. The people who are responsible for the end, for the price. So they are the person who invite the system and then need to do it in a perfect price, and then the client says, fine, I take it. With the Crystal Palace, the statics of the engineers started to get into this business, and not the feeling anymore. It's a prefabricated and pre-calculated system, and so glass wasn't used as a structural element anymore. It was used as a cladding for the next projects. And so these following projects are more impressive by their dimension, not impressive from the structural point of view looking at glass. The Galerie des Machines, a quite large building, 400 by 110 meters. This is a person. It's a three-hinged frame construction. Again, glass is just in cladding on top of the whole system. Other two projects, Lafayette, Le Printemps, two department stores in Paris, a cast iron system construction, and an inner and an outer layer out of glass, but it's only cladding. It's cladding with colors, but it's cladding. It's not structural use. The same way is the tradition of the modern architecture of the beginning of this century, with its breaking up the wall. The AEG tubing works in Berlin from Peter Behrens are one of the major steps by breaking up the wall, but it is a post and rail construction where the glass is just put in and being the cladding. It's not a structural use. The same with the tobacco factory Vanelle at Rotterdam. Or room height glass panels, large glass panels like these in the Villa Savoie from Corbusier, or the Farnworth House in Mies van der Rohe. You can move this, but the whole glass door move over here, but it's not a structural use. The system stands without the glass, and then the glass is just put in. Actual glass construction are possible because of the new development of material. They're getting more filigree well, more unspaced. What are these new glass materials? There are three things which needed to be said. It's tempered glass. Okay, tempered glass is produced by heating up the glass up to 700 degrees Celsius and then a quick cooling so that the glass is pre-stressed. There is a compressive stress, means the signs plus and minus are upside down in England, so you need to change it. This is a section through a glass panel, and then there's a pre-stress on the outer layer, and then there's a pressure on the inner layer of the glass. And when you put forces from torsion, like this, onto a glass, the pre-stressed surface needed to, the pre-stress needed to be reduced by this to a point where it is zero, and then the glass breaks. So this is a reinforcement of the glass, which is possible with this tempered glass. Tempered glass is not workable after being tempered, so you need to drill and do the size and so on before tempering it, and it breaks in these small pieces, which is a bit, which is better in one point of view, because when they fall down, they don't really hurt you very hard, because it's not like that size and coming down like in a cinema or something. The second, something newer product is partly tempered glass. I'm not quite sure if this translation is right. In Germany, it's called partly tempered glass. Partly tempered means it's not so quick cooled. The cooling is a bit slower, and so the forces which are possible in the glass are between normal float glass and tempered glass. But the breaking pieces are in a larger scale. So when you glue 2 times of partly tempered glass together, the breaking will always be a bit against the shape of the break pieces, will always be a bit against each other, so that fixed panel don't really fall down complete. This is the actual philosophy of safety when you use glass construction, not tempered glass, more partly tempered glass, and then glued together as a laminated glass element. Using using tempered glass made it possible to divide the structures, to separate structural system and glass layer from each other. First, you need a linear system with torsion forces to bury a glass panel. When you use tempered glass, you can do this punctual fixings, so you're able to get the torsion forces from the substructure into the glass panel, which is this and the moment over there. And you're able to do a normal forced substructure. Means there's no torsion in the structure, so it's less mass, which is this. And then, a sample for using this type of fixing. What I'm now doing is getting through the different possibilities of fixing glass. After putty, a still innovative method of glass fixing, because glass is fixed very soft and it's sealed too, so you get 2 necessities done with just one fixing method. Glass is now normally fixed with these, on the right side, sash bars. I hope this translation is right too. You see the size of the system is about 90 millimeters, 80 millimeters, which is quite a lot. When you want to get smaller profiles up to 60 millimeters, you can use pressed sash bars. Structural glazing, left side, is a bit a wrong word, because glass isn't used in structural. The thing does look like structural glaze, but it's only the surface. In reality, it's a post and rail construction where the glass panels are glued on, and in Germany we need extra fixings at heights of more than 8 meters. I'm not sure if it is here similar. It is. The hanging facade, or the hanging glass panels on the right side, that's a system developed in 1956 by Glasbau Hahn. It's very interesting because you hang a glass panel on top of its edges, and you don't have any bending problem when you stand it on its, well, this is a folded glass. When you just stand it, it's always able to bend. When you hang it, it's always flat, and you only have to take the wind forces for in and out. This system was used for quite a time, but then it disappeared because of the energy crisis and difficulties with isolated glass systems, and now it's not in use anymore, which is a bit pity. Then the bolt-holded systems. The first product named planar fittings is screw through a hole in a glass system. These are very rigid fixings, so the glass panel is extremely fixed, and when the structure moves a bit, there's torsion in the system, and so they developed these hinged systems with the hinge exactly in the glass panel, which made it possible that the substructure could move a bit without doing any torsion for the glass panel. This is quite an expensive detail. You see all the different screws. The cheaper way is to have a rigid fixing here and a hinged over there, but again this does some torsion in the glass. It's not so good as this one, but it's better than this one. This is possible for isolation glass as well. The development of the structures, the development of facade systems. The easiest facade system, a post and rail construction, top left, followed by a post structure, this one, and a post structure made out of trusses, and then the cable structure systems, a rigid cable structure with not hinged detailing here. The first hinged detailing here made a half soft cable structure possible, and the last development are completely soft cable structures with a flat surface of cables and flat surface of glass. On the left side, it's the Fondation Cartier in Paris, actual post and rail construction. Now this is also a post and rail construction, but by using these punctual fixings, the planar system, it's possible to divide the facade post and rail system from the glass facade by using steel angles, and then the facade is a bit before the post and rail construction, which let it look like being more filigree. Financial times, building a post structure with arms to carry the wind loads and cables to carry the facade loads. Again with a kind of punctual fixing for the glass panel. And again, the torsion of each glass panel is not in the structure, it's getting from the glass panel to the punctual fixing, and then from the arms in the posts, and so on. The same system with the columns on the inside is the car showroom from Hadi Teherani in Hamburg. Also here, this punctual fixings and the cable who varies the loads up into the post. Truss structure. This is a three-layered truss structure, the Louvre Pyramid from Pi in Paris. Three-layered because of, this is one layer of truss structure, second one, and then a ring cable who keeps the whole thing together so that wind suction don't take it out. Okay, now the cable systems. This is a hard cable system. It's the concert hall in the Börse van der Lage. It's done by Peter Zanem and Mike Eckhout. Rigid, fixed bolts to hold the glass, and then this is a rigid, hard cable structure because there are, very little movement. This is in a hole, so the pre-stressing forces don't really need to be so high because there is no real wind load, but still a person could lean on, and then there are some loads, so they need to reinforce the system. Yeah. And then 1982, from Feinsilber and Reiss, Francis and Ricci, the Science Museum in the Parc de la Villette, Paris, they developed this hinged glass fixing here and made the system movable a bit, so it's a half soft system. So when there is wind pressure, this cable gets a bit longer, and the whole facade could move in a little bit. And by wind suction, the same upside down. These are 2 by 2 meter glass panels, and 8 glass panels are fixed to each other, so they completely hang in like a curtain, and then they're fixed here with was heißt eine Feder? Springs. Yeah. So there's springs here because if they damage 2 glass panels here, the whole system would maybe get a progressive collapse. Means it just connects complete, and so they did the springs here, and so the whole system moves a bit, but it's a type of soft. This system is now very fashioned. This is Waterloo Station, London. Everybody will know it. It's an old structure where they put this new glass wall in, and I showed this slide because you can see that by pre-stressing the cables, there are a lot of forces which need to be taken somewhere. When you get an old structure, you can't put these forces into the old structure, so you need another post in the middle of the system to take these forces. And well, then you see what type of forces and what the size of the forces is that you really need to fix them somewhere. Channel 4, also in London, again, various layers of cable. This one in the middle of the arch for wind pressure, and here in the edges of the arch for wind pressure it's in this way, and for wind suction it changes complete, so it's a lot of cable work in this system, which makes it difficult to understand how it really works, and maybe that's what we wanted, I'm not sure. Avenue Montagne, again from RFR, done with Eiffel. For the wind pressure, horizontal cables, all the glass panels are fixed to each other like a curtain. These are the largest glass panels I know. It's 3 meters by 150, only hold with 4 bolts, which is, well, that's the end of the possibility, I'm sure. Cable for the wind pressure, and back cables into the building for the wind suction. What they try to do is with this flat glass surface to get this yard round for the whistle. Now soft cable structures, first developed 92 or something. The Kempinski Hotel in Munich. This is a view through 2 layers of glass structure. It's a complete glass, flat glass surface, and it's a complete cable surface, flat, behind the glass surface. So you need to have a bit of soft fixing for the glass panels, because the whole thing moves in a meter by maximum wind pressure. Means get to the wall, move it a bit, run around, take photos, an hour, come back, and the wall still moves a bit, which is here again you see. And the cable layer is exactly in the layer of the glass panels, so that it's well, it's a maximum height of transparency. It's 98% of glass, and the rest is, well, some kind of joints. The other way is trying to use the geometry of the structure, Archstone Constructions or grid networks. They are more effective because there is less torsion, and so the mass of the system is less. The systems are pre-stressed with cables, 2 ways of cables. These crossing cables, because they have the problem that the whole system moves a bit in this way, and then these like a wheel of a bike cable systems to well, when you got this barrel, it started to deformate a bit, and so you need these separate systems in the middle to get it back in the right way, so it is really a barrel. This is the project in Hamburg, the New Museum, which is done by Gerka Mark and Partner, the architects, and Schleich Bergermann and Partner. And again, here is an architect who has a client, and an engineer who has an idea, and a builder. Fischer was the builder who has the possibility to do it. And these three people together made this possible in a very short time and at a very cheap way. This is again the group you need to do proper and new developed systems. Here you see again there's a kind of dome in the middle, and these are the glass panels, and when you get where both barrels get together, you always get synclastic areas. We can't really use a glass panel in one piece, and so they just cut them in the middle and glued it again, and that's it, how they close. The glass industry wasn't very happy about that, but they just said we do it, and it worked. Second project done in this way, again a barrel. It's a spa in Stuttgart. Schleich Bergermann and Partner had been the engineers again. This is a barrel which is a bit curved, not only in one direction, in two directions. So it's again a bit synclastic curve because of these cable structures. So by using this synclastic curving, the structural energy of the geometry is getting better. This is also possible. The system is also possible as domes. Aquatoll again, it's Aquatoll at Neckars-Ulm, again Schleich Bergermann and Partner. The same principle, again the steel network and the cable grid. And when you look here, you see these strange formed isolated glass panels, which is a bit difficult from an architectural point of view, because it's not rigid formed. A bit better system is this one, which is an office building in Berlin from the same builder. It's a dome construction in the middle, synclastic formed, with an anticlastic areas at the edges. And here you see that the glass panels are triangle, but from the architectural point of view, it's the right way to get this structure to its end. The curving isn't so much that you do have to cut the glass pieces, because every glass panel is, was heißt windschief? Forget it. Okay. To dematerialize structure more, you have to use glass as a planned load-bearing structural element. Only few projects had been developed. I start again with simple beam structures. This is the hanging glass facade from Glasbau Hahn, which was developed very early. And this is the Lehmbruck Museum in Duisburg. It's only 7 meters high glass panels, stabilized for wind loads by glass fins on the inner and the outside side. They did this system up to 13 meters in the Frankfurt airport. And the glass panels are fixed at the top and then just hanging, and the bottom, there's nothing, just a bit of stones. Other project, English project done in 72, I think. Ipswich. Also here, this is a complete hanging glass facade, and it's stabilized on each slabs by glass fins, which, and then there's this special detail which allows to move the glass facade by different temperatures, higher and lower. I read an article about difficulties from the last 20 years, and they said they got 3 or 4 glass panels collapsed during that time, but always at the bottom of the system and not at a higher level, so there was never any damage for people. Beams and columns. This is a beam and column system, a very easy beam and column system. The Winter Garden at London Hampstead. Rick Mattow was the architect. It's difficult to get pictures from this. It's a column and a beam laminated at this edge, difficult technique, and then cladded with glass panels as wall and roof. Next point is a glass frame system. This is a black and white picture because the exhibition pavilion in Arnhem doesn't exist anymore. It's broke down. It's end fixed columns with a cross, so the whole system is a beam, a frame. The beam of the frame is done by steel plates and then just screwed through the glass columns. We did in our university in Aachen this glass pavilion. Again, beams and columns fixed together as a frame. This is now an exhibition pavilion for our university. I'll show more later. And a very exciting beam project is this one. This is the glass beam who is bearing the bridge. It's not usable for everyone. This is a connection bridge between an architectural office here and here, so it's for the architect. It's not for everyone. It's the only project with real glass columns I know is the City Council at Saint-Germain-en-Laye. It's done 1995. The slides are on the wrong way, because when you see them together, you really get the imagine of a complete room without real columns. They are there. You can see them because of the edges of the glass. You can't really get them invisible. But it started to disappear, the column. The column takes the forces from the substructure, the steel substructure which carries the roof. It's 4-meter columns, cross section. Truss system. Again, this is a London project. The first stair at Joseph's shop von Eva Jirichner. It's a simple truss structure. Glass layer here and then a plastic step on top with just one post here and then wiring back and the reinforcement into the glass panel. The project we did in our university is this truss structure, glass panels here, and then the top glass panel who takes the pressure of the system and some wiring below to do the trussing. Third project we did in Aachen is this truss system as a facade system with the glass layer in the zero zone of the truss system and 2 cables on the outer side. It's done like when you take some books from the shelf and you press them together. You can move them as you want it. And that's what we do with the glass panels. They're pressed together and then fixed. The idea of the facade is from this project, which is in the, how is it called, Flight of the Crane sculpture in Munich, done by Santa Rosa. It's broken down now. It's again a truss grid system, 3 grid layers, which pressure forces are put into the glass panel in the middle in the zero zone of the truss structure. Glass arches. The only real glass arch project I know which is which is current, is the Lindener Bank in Hanover. It's a 3-hinged arch, 1, 2, 3, which bury the glass panel, and then there's some extra steel for safety reasons to be sure that if this bit of the arch is breaking, it doesn't disappear in some kind of direction, so they needed this steel, which started to make the thing worse, because you're not quite sure if the glass really is carrying it or if you're able to just use the steel system. It's a bit of pity. We did in our university again a glass barrel with pre-stressed cables who just fix the whole system for normal forces. Later more to that project. Glasbau Seele did this office building in Augsburg. It's a dome out of glass panels. Also here the forces are getting through these points and a plastic bit in the middle from one glass panel into the next glass panel, and so the whole dome is pre-stressed with a cable system beneath it. When you look at this, you see this is isolation glass, and isolation glass plus joint means always 4 centimeter black joint. When you use a steel grid network, like the one in Hamburg, it's also 4 centimeters steel. So it doesn't really make a difference when you use this system or when you use a steel system. But this does cost 4 times the other one. So explain it to the client. Domes, complex three-dimensional glass structures are the next step. This is an inversion of the tree-column principles. The forces do follow the cable like they follow the arms in a tree. It's a cable truss canopy at a concert hall in Eindhoven, again done by Mick Eckhout. Another artist who is doing really interesting things in three-dimensional glass structures is James Carpenter. The left is a Philadelphia project and the right is a Munich project. He's working on this Buckminster-Fuller tensegrity principle, three-angled glass panels fixed here and then an interesting wiring system around it to fix it all together. It's difficult to use this for more than just art or sculptures. And this is a bit architecture. As a three-dimensional glass structure, it's the inverse pyramid in Paris from the Louvre. Again, each glass panel is fixed to beneath each other, and so they hang complete. But they're not hanging in this direction, they're hanging in this direction. So there is a bit of a buckling problem in the middle. Therefore, they needed a three-dimensional cable system, which you can't really see when you're there because they're so weird, wired, running around. It's difficult to use. It's a sculpture. You all maybe know the picture of the poor guy who is trying to clean this here. It's three-dimensional structures are difficult to use. There are 3 ways to use glass structures to get more filigree, to get more transparency into the system. Use the reserve of the system, minimize mass, try to get away from torsion, try to get normal forces. Second, activize geometry, try to get away from torsion, try to get arches, domes. Or third way, use glass as a structural component, as a structural load-bearing component of the construction. The difficulties are rapid failure without telling before. When you get steel, you can see short before it breaks, it gets a bit thinner. When you try to break a normal wire, short before it breaks, it gets thinner. There is a performing zone. Glass doesn't have this performing zone. It just off it is. It's a very dangerous material, and that's the reason why everybody is so cautious, so everybody is afraid about glass. Well, second, that makes the problem of admission. It's always difficult. It's in England difficult, in Germany, it's in whole Europe. It's extremely difficult to get glass structures for public use done. You always have to do a lot of testing, costs a lot of money, nearly the half of the project price. So it's really a problem. But still, glass has enough reserves. It's possible to use it. Forces must be put into the glass controlled, so the detailing must be done very carefully, and that costs the money. From a structural point of view, our complex systems with controlled load-bearing function for glass are possible. And now, second part of the lecture. They need to change the slides. What I'm showing now is are the 4 projects we did in our seminar. The seminar is called Glass Constructions. It starts with a theoretical part where we get the students to report about historical and actual glass construction and about the constructural dependings of glass. We do this to get an idea of the logic to build with glass. The second part is always to build with glass. This is done to get with the students over the level of just planning it. We really want to do it. That's our concept to get teaching, research and practice together. The first project, the first two projects are done in 1995, so 3 years ago. It's the glass pavilion and the glass roof. They're both planned in the seminar. The groups of students who built the things had been led by Thomas Link and Michael Tümmers. So they are both students working in my team as tutors. They're students, 6th, 7th semester students. The sponsoring, and that's the second thing, we don't have any money for this. We only can buy some screws. The sponsoring is done by some big glass companies. Glass Pavilion is sponsored by Facade, a related company to Saint-Gobain, a French glass company. And the glass roof is sponsored by Flachglas, related to Carpenter. This is the glass pavilion, which is done for the celebration of the 125 years of our university in Aachen. It's placed directly in front of the university main building in a fountain. The concept is a modular system or, as a glass cube which could be additional enlarged. The principle is glass carries glass. The steel elements, you can see, are only for fixing the glass panels in their position. So every bit of glass carries themselves and the bit of glass on top of it. The system is 250 wide to 625 long and 250 high, and it's stands on a two-piece U-section, these two pieces of U-sections, and then there are these fixed end columns, laminated, tempered glass, 3 times 12 millimeters, which are fixed with these bolts in epoxy putty to be able to demolish it later, to take it down very easy. Then the cladding is normal tempered glass, again fixed with these angles and bolts through the holes. The Fegler was quite generous by sponsoring all these special details, which costs, well, for every screw you need 10 pound. It's quite a lot of money. All sponsored. Safety concept. That's what you always have to do when you do a glass project. Safety concept is here. This is not for permanent use. This is on our private university space, and it's placed in a fountain. So it's difficult to get there, and people who are in there should always wear a hat when they place something. It's not for public use. Again, the column and the fixed end column with some lashes here for the loads and the screws for the wind loads. And here you can see the angles with long drilled holes, so it's possible to move around a bit to get the right position. The corner of the beam, here this 3-layered column, and then 2 6mm layered glass beam on top, just fixed by this screw so that it don't break down. The door. Fegler is quite proud of it because this is a silicon door hinge. This is a glass panel and this is a second glass panel, and this is like a saloon door which is just glued with a silicon joint here, and they said it's about 100,000 times of changing direction without any problem. By gluing it in a machine system which normally does the golf front windows, they had been able to make this panel being in a flat surface. The silicon joint is really interesting. You can cut the silicon half of the depth of the joint and still move it around, and still it doesn't start to break down to leave the glass or something. It's good material. The fixing, we haven't had any technical support, only manpower. 60 students needed to be through this project in 2 weeks. And so you really need to think carefully about what to do first and how to do it, and so that no one is really injured by doing this. And we did it after the term. There were, well, not so much people, and the fountain was without any water. On the right side, this is Thomas Link putting in a profile in between the glass panels. Normally you need to do perfect, proper T-section profile here. Costs £10 a meter. You need to take 200 meter, which is too much. So I went to just a shop next to the site, bought a Schlauch, a pipe, the one you use in the garden to get the flowers wet. Hose. Which is possible in trans. It's transparent, and you just put it in. It costs £0.5 a meter, and just it's fine. Well, you can't sell this to a client, but for our private use, it's okay. Topping out ceremony. It's a strange feeling to be inside this, and the whole seminar tried to get an idea of this. And on the right side, you see the whole seminar, some official from the university and from the glass company, and so on. Second project was done in the same year, the glass roof. The concept here was there was a brick ruin on our experimental area. Our department has the possibility to do some experiments in a certain space. We put on top of this brickwork carefully a glass construction, a glass truss construction. The compression forces of the system are in the glass panel. We try to get rid of drilled holes. We try to get the forces from one glass panel by friction into a steel plate, and again by friction into the glass panel, but not by drilled holes, because drilled holes always cost £10 a hole, means nearly the price of the glass panel. This is the system. It's a truss system, 3 by 3 meters, with its cross bracings and columns. Safety concept, again, this is on our site. This is private. No one can really touch it. But we did calculate punctual forces, which is a problem for this system. A punctual forces of 150 kilo means 2 people on just 1 point. And we did some tests with these forces, and the whole system moves just a centimeter, which is fine for that project. The details, the bottom point is done with a steel angel, which is drilled with a bolt drilled into the brickwork. That's a very carefully touched, and then with bolts through the joint, and then friction from a special plastic material into the glass, and up it goes to the edge point, and there the same detailing. You see, this angle is shorter than this one. That means the forces, the horizontal forces in the system, are double of the vertical forces of the system. The cross bracing done very easy, just easy cables. This U screwed here, and this is a pipe just fixed together, drilled, and then the screws gets through. We would like to do it in a proper, better way, better detailing, but we always have to buy this by our own. We always have to get cheap detailing done, and that's the way we do. The special plastic is used for normally used for oil pipelines. Means for fixing 2 bits of oil pipelines, you use a plastic which is possible to get very high, is able to. Das muss sehr heiß werden können. It needed to be able to be very hot, and it needed to be able to be fine for 20 years or something. So it's not very compressible, but it takes the friction forces very good from the glass into the steel. So the friction is on the glass panel is very good. The fixing of the system is done by scaffolding out of timber. We put on the glass panels, we fixed every bit of steel structure, and then we, how's it called? No? No? No, you don't have to move the slides, I'm just looking for the word. Well, we reinforce the cross bracing so that the system moves up from the scaffolding a bit, and 2 centimeters. So we looked if it works up fine on all sides. It's the same, and it's done like you do your guitar. It just my boss was standing there, and he said, "Well, this one, a bit more here, a bit more there." And then the whole thing moves. You break down the scaffolding in 20 minutes, and then there is this engineer moment when you feel, well, the bridge works, which is very interesting as a feeling. It's now, well, then it was finished, and we did this testing with asymmetric loads. There had been no problem. It's a very small project. It's demolished now because we used the space for our third project, the facade for the faculty. The whole project is a library building for our faculty. We have an enormous space problem. There are not enough seminar spaces. And so we decided, 3 people, Wilfried Führer, my boss, Yvonne, and a colleague of mine, and me, we decided to, well, try to get this building done by sponsoring. So all the materials for the whole project are sponsored by the industry, and the project is built by students of our faculty. 70 students built this building. I got a slide. This was done in 1906. It's now nearly finished after having done well, all the walls and all the cladding. Now the university took the response for a bit heating, a bit sanitary. That takes now 2 years to get this in. It's a bit, well, how it works. The glass construction of the facade is again planned in the seminar. The statics are done by Wilfried Führer, Yves Weiner, and me. The leading of the student groups are done by Valerie Spalding and Mario Hunkel, both 6th semester, 3rd year students, which really get to the edge of their possibilities, personal possibilities, by leading 60 students getting through this thing, and no one was fallen down, no finger was a break, nothing. It worked quite well, but a lot of sleepless nights. The sponsoring was done again by Fegler and Weller, which is a steel builder next to Aachen, and several smaller bits and pieces, the silicon and the lamination, and it's a lot of things. The concept is a glass and steel structure. There should be no forces into the external building structure. It should be an independent and self-containing system. The system is pre-stressed, means normally in a truss system you got pressure here and suction here and stress here, and we pre-stressed this pressure here into the 0 zone of the glass panel, the thing with the books when you move it. The target was an extreme cheap product with punctual fixing. Extreme cheap because we didn't use any drillings. We went through the joint with the screws, which needed to fix the steel plates on both sides. The system is 20 meter by 6 meter high. It's the pre-stressed truss system. The compression load is about 2 tons per system grid. It's 7 panels on each other. The panel size is 80 centimeters by 2 meters, and the panels are 2 6mm tempered glass, means just normal window glass, only tempered. Safety concept, because this being for public use, we needed to get through the normal regulation way. We did the safety concept, means we did some testing with glass panels, with pre-curved glass panels, so that the bending problem is more than it is normally. And then I asked the guy from the glass company, how much forces do you think we should take? 2 tons in the system? He said, well, 10 would be fine. I tried to get some measurement instrument for 10 tons. We put on the 10 tons, the measurement instrument went off, the glass didn't. And then we did this pre-curving in one direction and into the other direction, so the whole glass is really, well, moved around, and the 10 tons worked fine. We demolished one glass panel of the 2 layers of the glass panel, and then 6 tons were able, and tie kick in the middle, and nothing happened. So we are quite sure that I could put my daughter under it and nothing happens. Detailing, it's These compression plates, it's simple steel plates, just drilled, very simple, very cheap elements with these arms in a triangled way, because so they don't twist, the whole system doesn't twist. And an 8mm cable here and a 5mm cable here, a special fixing here, which makes it possible to reinforce the system by drilling this in this direction. So we don't always need these ends here, which does cost more. So it's just 4 cables for the whole system. When the lorry came with all the material for the thing, it was just, the steel material was just the size of this table, that's all. So, well, we looked on the lorry and we thought, well, this is not enough, we need more. And then we completed it and it worked. The fixing again is done with this timber scaffolding. Here, the facade is leaned in about 7 degrees, about an angle of 7 degrees, which is good because when you got the timber structure, you just can lean on the glass panel by taking it up and fix it a bit so it doesn't fall down very easy. And then we fix the steel plates and all the things. And again, there were this the reinforcement of the cables had been done by a measurement machine. The measurement machine you normally use when you put, was heißt Mast? Vom Segelboot, der Mast. A sailing boat. This column in the middle. When you put the 2 cables on the side, you need to check that both sides are the same. If you don't, well, the column gets curved and it's dangerous. So there are very easy measurement instruments where you can check the forces. We use them here, and then again we set silence for a day on site, and then we did this guitar thing, because using your ear is more exactly, it's more fine-tuning when you use it by the voice of the steel cable. So it's the first measurement done with machine and then done by listening. And then the takedown of the scaffolding, and then again there's this engineer moment when you take down the scaffolding in 2 hours and the whole facade is fine. We wanted to use rough steel in connection with these precise industrial material glass, because glass is done perfect on 0.5 millimeter size, and and this is real rough steel, very hard. We didn't really want to use these high-graded steel you normally use by doing glass structures. Also, we needed to show that we are able to do glass construction under regulation rules and for public use. And the second thing, we needed to show that we are able to do glass construction in a size which is not, so that you can't say this is just an experiment, you are not doing proper. It was hard work because there was no money. The whole thing is completely sponsored. We had for the complete building about £3,000 for some screws and a crane, and the rest was sponsored. The last project done last year is this small glass barrel. That's a project we wanted to do. It's about 6 meters, and we used the glass from the glass roof, which was taken down. Now this is 3 by 3 meter. It's a polygon arch out of 7 glass panels, stabilized with a stressed cable beneath it, and asymmetric loads are getting into the steel plates, like in form of torsion. The glass detailing, you remember this grid shell system, this grid net system from Schleichbergermann and Partner. This is a way which is in mind of lots of people since a long time. We've been able to do it here. It's the forces are from going from this panel through a hard timber bit here, again in this panel. This could be plastic later, but the guy who did it was better in use with timber. And then we got these edged glass steel plates, again with these special plastic, and some screws here, and that screw makes it possible to get the reinforcement forces, not by drilling here somewhere, by drilling here. And so you can do the forces especially at that point where you want it. The normal grid network has the problem that there's one wire through the whole system, and by friction you lose the torsion from the way where you start up to the middle. So the whole thing is a bit soft in the middle. By using this detail, you're able to say exactly, I want here more forces and there less forces. We did, again, this is the scaffolding with timber, which needed to be done to build the thing. And then we did some testing with asymmetric loads, which is really a difficult thing for this system. Don't worry, there's a safety cable. We put 300 kilo on here, and the system moved down a centimeter, which is fine for the whole system. The next thing, the larger one we would like to build, we do again this cable system in the middle, like the real one, the one they used in Hamburg, this one here. They call it cable sun. That's the glass panel under beneath. It's a glass barrel without supporting structure, steel structure. Because of being glass plates, you don't need any cross-bracing cables. You can use the cables in the joint of the system. But also you see the joint is about 3 centimeters. Well, you can do it smaller, maybe by 2. But when you use isolation glass, again, you got this silicon and aluminum profile here. And so the whole thing starts again being 4 centimeters. And then there's the question if it does make sense to use this. So using glass as a structural element is easier when you just use one layered glass and not isolated glass. That means you can't really use it always for public uses. Well, I'm going to finish. I do believe that in future glass is more used now as a structural element with wanted and controlled load-bearing function. And this is necessary to create more effective and more transparent systems. My professor Wilfried Führer wanted us to push the edges of possibilities. That's what we try to do with our work. Thank you.
Am I allowed?